Thanks for the hospitality and for the invitation to this beautiful place. Nice seminar. So initially, when Madhu emailed me, I had some other topic in mind, which I thought I would have complete some work on that, but I couldn't finish my work on bulk reconstruction. So I'm sorry, I have to rehash my talk on NSM 2019. It's more or less an extended version of that talk, so I apologize beforehand. People who have seen this before. Okay, so this is some work which recently concluded with collaborator Ji Ren and Sun Yat-sen University in China, and my student Gaurav Katoj at IIT Hyderabad. And in some sense, this is completion of the work we started in Hebrew University with Eliezer Rabinovich and Stefano Bolognesi. So, okay. So by way of introduction, just something highlights which everybody is familiar with in holography. So the way we understand holography right now is that the bulk geometry is kind of an encoding of the boundary state entanglement structure. This, of course, most of you know, this started with this path-breaking work of Ryu and Takanagi in 2006, where he showed that the boundary state entanglement entropy can be written as some kind of a geometric surface, some kind of a maximal surface in the bulk. And then, of course, a bit more recent work by Molsheim and Susskind, which is titled ER equals EPR. So an Einstein-Rosen bridge, which is a geometrical feature in the bulk, is equal to some kind of a EPR, bell pair entanglement in the boundary. Ramsdong, of course, put this into a slogan a long time back, where he declared that space-time connectivity or spatial connectivity should be thought of as some kind of entanglement structure in the bulk. So this is the theme, the overarching theme on which my work, I would say, falls in. So the prototypical example which we turn to over and over again is the example by Molsheim in 2001 of the eternal ADS black hole. This is like the prototypical example of this notion of bulk geometry being equivalent to some kind of entanglement in the boundary. What we have here is an eternal ADS black hole, which is supposed to be represented in the CFT by maximally entangled two CFTs, which are entangled in a very specific fashion, which I don't have it. So this is an example, two things being entangled in the boundary CFT is given representation in terms of bulk geometry. So of course the bigger question is the reverse. Can I recover entire gravity, the dynamics of gravity, from looking at boundary state entanglement? And there has been progress in this area as well, beginning with linearized Einstein equation in this work, and then some nonlinear terms in Einstein equation has also been, perturbations also been recovered from the boundary state entanglement using first law or some other versions. So slowly the picture which is emerging is that perhaps you can recover entire gravity from looking at entanglement properties of the boundary state. So one.
So this example of the eternal ADS black holes.
Yeah.
And some cousins of them, they are supposed to be rather special examples of entanglement.
Yes, but that's true. But then there is this also different data in which you can recover dynamics of Einsteinic field equations or some linearized and come corrections to Einstein field equation, which also come out. This is this is the advertisement. You're true. These are very special examples. But in general, the idea is that if you give me the boundary state entanglement structure, maybe I can recover gravity or geometry from it. This is the idea. So of course, this is a very special example. But this is again the first example.
I mean, this is only a criticism that I hear of.
Yeah.
I mean, I'm not. So how good is this criticism? I mean, it's like if you have a generic entanglement between two field theories.
I think we are in the process of discovering that. I think that is not the final word. This is what I want to say. I don't want to, yes, because this is one example which I use as a propaganda, but yeah, it's true that. But we are in the process of figuring that out, whether in general how much entanglement dynamics codes geometry. I think we're still in the process of figuring that out. Okay.
Just to reiterate, suppose you evolve both these field theories along this time.
Right.
When this tube becomes sort of longer and longer and thinner,
that's right.
So these spaces become less and less somehow coupled to each other, even though the entanglement is not changing.
Right. So what are you saying? It's a choice of frame or a choice of.
I mean, saying that the state at zero time is entangled, and it brings the two boundaries, within reasonable distance of each other.
Right.
The state at late time, if you evolve not this way, but both up.
Both up, okay.
Okay, is equally entangled, but the two things get more or less disconnected. It's the distance between the two boundaries goes to infinity.
Yeah, so that is where complexity comes in. That the fact that this is lengthening, this is what complexity is supposed to code.
Yeah. So I think what Gautam was saying is that it doesn't seem like entanglement itself is enough. It seems like entanglement plus plus.
Sure. Yeah, computation complexity is like, that's true. Yeah, yeah, probably I agree.
Could be that say you have three systems and you give me a very specific entanglement structure among them. You can ask that is there any gravity theory for which those
You mean a geometry, some geometry.
for which those will be bounded. There might be an answer that may not
Yeah.
be possible.
Yeah, so I mean, I don't think we have decisively answered those questions. These are like bits and pieces of some data we have, and which we're trying to, see whatever the full picture is. So what I'm going to talk about, of course, is not entanglement, but some, from extension of that, this notion of something called computational complexity of the CFT state. This is not a usual kind of observable which we talk about in quantum field theory. In quantum field theory, we are generally indoctrinated to talk about things which are independent of the regulator scale, but it'll turn out that this is some quantity in which you can never get rid of the regulator scale in some sense. So, but this still plays a role in the geometry. It's still a physical quantity in that sense. So what turns out is that spatial volumes in the bulk will correspond to this kind of feature of the CFT state, which is known as computational complexity. And again, we turn to the prototypical example of the eternal ADS black hole to come up with this or to see how this happens. What Shiraz was talking about, this late time volume of this ERB slice, if you take the CFT evolve in up direction, you might wonder what CFT feature controls this aspect of the geometry in which the length of the wormhole or the ER bridge is increasing with time. Okay, so you might ask, if ADS is really dual to CFT, which CFT data govern this behavior? And it turns out this is the answer to this is this computational complexity, or this is one of the proposed answer, let's say. So this complexity quotes this ERB volume, and the supporting argument comes from this equation, which is dc dt equals Ts, or approximately equals Ts. So the time rate of change of complexity has a specific behavior, and it turns out that the ERB volume, if you plug in here, it indeed satisfies this equation up to dimensional, Einstein-Rosen bridge volume. So the cross section times the So this is the sort of insight which led Susskind to propose this.
dt is equal to Ts.
Yeah, so this equation, this is something you get in computer science. There's no strict derivation of this. The fact that both sides are extensive makes you put this factor S on the right hand side. And this T is actually a placeholder. You put it for dimensional regions. You could have put energy, ES, but then it doesn't match with the behavior of, let's say, charged black holes. Black holes in the limit when they turn extremal, this equation will be violated. So TS seems like the better formula. dc dt equals TS seems to be the correct formula.
So what is the state you are considering? It's Thermodynamic double and then two operators one acting on right and one acting on left.
No, there are no local operators which are inserted or anything. This is some non-local quantity in the boundary.
What is the state in the CFT for which you are computing the complexity?
The CFT state is this thermophile double state. So e to the minus, let me just write.
Where is T dependence coming from?
T dependence is coming.
T dependence is coming from where?
Coming from the, so you can think of it, small t is the difference between T1 and T2. So T2 runs downwards.
For what? Are you inserting an operator on right boundary?
No, there are no, this is not a local operator construction. There are no operators in this state. Just normal time evolution.
So you are time evolving the state, one right side is going up and left side is going down?
Right.
That will be a symmetry. Further nothing should happen.
No.
I think you are going up.
Both
Both up.
You are going up.
T1 minus T2.
You are going up on both sides?
Yeah, that's right. Otherwise, this geometry would be completely time independent, right? But the fact that the ERB volume is increasing, then nothing would capture that. If you consider T1 plus T2.
I understand. If you are going on the opposite direction, then that's a symmetry, so you will not have anything interesting. So you are going
No, that is still geometry, but it won't code this growth of the ERB slice.
Right. So if you are going on both sides in the same direction, then you will get something non-trivial from that state. Your computing complexity of that state, that is supposed to be equal to this area of this.
That is the conjecture. That's right. That's right.
So does this complexity also depend on the factorization?
Um,
Are you thinking of this state as being a state that is living in the direct product of the Hilbert space from here and Hilbert space from here, or you know, in order to define
no, you entangle. You have to entangle. You cannot take just the product states, factorized states. It has to be entangled. This thermofield double is an entangled state.
Computational complexity in it has the structure of a. So in order to define such a thing, you need first of all a Hilbert space that is direct product of two Hilbert
That's
spaces,
right.
And
That's right. So most of the times in geometry, what we will have will start from an unentangled state with complexity 0, taken to be having complexity 0, and then we'll compute. This is how in field theory. I'll just show.
Shubho,
Yeah.
I have a nice question. Do you assume at any point that the theory in the bulk is some Einstein's gravity?
No, the whole idea is to, you know the geometry, you know the metric, but the solution which determine that metric you're supposed to get from the boundary field. That is supposed to be the emergent.
And S was what? So the S was what?
This is the entropy. If you have a finite number of degrees of freedom or a state which has finite entropy, like CFT on compact volume.
Entropy of which? Sorry.
This equation applies to a quantum mechanical system. General quantum.
So in this context, what?
It will be the CFT because CFT and this is the bulk and this is the boundary quantity.
No, so S is like the entanglement entropy of the right CFT. Is that what you?
No, S is the. So this is the system at finite temperature and finite entropy. CFT.
The system becomes at finite temperature only if you integrate out the left.
That's true.
Otherwise, it's a pure state.
Um,
Entropy will be 0.
That's true. But this equation, here this S, if you compute for this geometry, this S would be the Bekenstein-Hawking entropy. So this S, you can ask in the dual theory, in the thermofield dual picture, what is this the Bekenstein-Hawking entropy? And of course, it turns out to be the, if you integrate out one of them, then that is the, So
that's the entanglement entropy of the right.
that's right. Okay, so this is just, propaganda, but this is the outline of the talk. So this is what I'm going to talk about. I'm going to try my best to define this in quantum field theory, and we will see this is very limited, our expertise in this. And then I'm going to talk about the complexity volume and action conjecture. I come back to holography. This is non-holography part of the talk. And then I'm going to talk about cosmological singularities, which were engineered by these authors. These are the kind of singularities we study and try to understand what complexity has to say about them. I will then compare the CV and CA results and try to draw some lessons for appearance of, say, spacelike singularities and what do we understand about them from the complexity analysis. And then I'll talk about more recent work which I've done, try to understand time-like singularities in the bulk and what is the understanding from the CFT side. And we will try to compare our results with the well-known phenomena or well-known criterion in the literature, which is the Gubser criteria. Okay, because we already have some kind of idea from CFT what kind of time-like singularities can we expect to arise in the bulk, and we will try to compete or compare with their result and see what we get. Okay, so this is the last one. Okay. So computational complexity in quantum systems. The idea, this idea is borrowed from the computer science literature or information theory literature. The idea is that it quantifies the difficulty of performing a task within quotes, because it's a highly qualitative, subjective idea. So what are the ingredients which go into the definition? You need a system, a set of states, some reference state, and some simple operations which take you from one state to the other state. Okay. And the complexity of some state, let's say A, is given by the minimum number of simple operations needed to go from the reference state O to origin to A. Okay, so this is a very qualitative way of defining. And Classically, if you look at a system like if you have n classical bits, let's say I'm talking about a system of n classical bits, and I ask, then I can take the reference state 0 or O to be 1 in which all the spins are down. And then you can ask, let's say, this target state A, which is usually called a target state, could be like, let's say, a subset of the spins turned flipped up. And you can ask what is the complexity of the states. And you can say that, okay, I have to flip m spins. So the m would be the answer to this. M would be the answer to the complexity. And it will turn out that there's no difference, big difference between the entropy, which is the total number of states, which is 2 to the n, which you take log of that, then you also get the similar. So classically speaking, we don't need to invent this concept. Entropy is good enough. We don't need to invent complexity.
Sorry, what is n?
N is, let's say, a system of n bits, classical bits.
Number of lines points.
Something like that, degrees of freedom. However, this whole thing drastically changes the moment you bring quantum mechanics into the game. Then quantum mechanically, entropy doesn't remain the same really. It scales with n. However, due to now you can have all kinds of states. I don't have a chalk here, but basically superposition. So up and down, you can make many such superpositions. As a result, the number of states will increase in quantum mechanics by exponentially. So this complexity captures this part which entropy fails to capture. Okay, so this is really a new concept which captures the entanglement. So these coefficients capture some kind of entanglement between these two states. So superposition of these two states. So this is kind of a novel feature which is the quantum mechanics brings into the game. There's another sort of pictorial idea, so schematic graph how complexity is supposed to evolve with time. So this is complexity plotted against time. So you see initially there'll be a linear growth, a conjecture linear growth, which is the dCdt equals TS region. This is this point n to the p, degrees of freedom to some power p is actually the point where entropy saturates, entropy becomes maximum. But the system in some sense still evolves because the complexity keeps on growing. And it goes on till this kind of a time, till which it reaches a saturation. And then it spends there a long time, because the reason is if you compute the complexity of some bit systems or systems like that with large number of degrees of freedom, it happens that most of the states are maximally complex. So that's why this is a very long time. And after this Poincare kind of recurrence time, again it starts to decline, okay, and you come back to 0. So this behavior, this part, this plateau is because most of the states in this quantum system are highly complex. So entropy saturation.
Quantum case, how would you count the number of operations, like how we did for?
I'll come to that. So this is the kind of expectation which we have. Let me just. So how we actually do it. So this is the idea. You have, instead of classical state O and A, I have two kets. The reference state and the target state, and there's some unitary transformation which I'm using to relate them. So this unitary transformation, of course, you can take, let's say you have n spins, and now these are quantum spins, so you have to write them in kind of tensor product form. And then you can, of course, do it at one step, but we won't do that. We would use something called a gate, in which, let's say, we will couple at best coefficients of 2 of them at a time will change. So these are called these are special unitary matrices which don't involve a lot of spins. So these are kind of limited unitary operations. And we will try to build this U out of a product of many such 2-qubit gates. Okay? So this is the idea. So you could have done this in principle in one step, in one go. But instead we will do with 2-qubit gates. And then let's say
Specified 2-qubit gates?
you can use 3-qubit. You can k-qubit gates. You can.
That's fine, but just within a particular set of qubits, there's some specified set of unitary operations?
That's right. That's right.
Like some finite number?
Yeah, there's some finite number of them. So I'll use Nielsen's idea in which he converts this problem into a geometric problem. You can represent the states and these operators U in some kind of a manifold, group manifold. And then you can write down an evolution equation for this gate, series of gates. You can write down an evolution equation which is given by this. This is the evolution, the control Hamiltonian which we evolve from initial state to final state. And the idea is the initial state, because the reference state u at time t equal to 0 is identity, because you're starting from the reference state. And at the end of the process, you get to u. So this, if I draw this, so you apply n number of gates to get to here, and this is supposed to represent some kind of a curve or a path, trajectory in this set of all operators, u operators. We also need to define a notion of a cost function, which is what will give you the complexity. So it is something which depends on these coefficients, which the coefficients are the tangents, these gammas are the tangents to this. So you need to integrate this and define a distance. This is given by something which Nielsen calls the cost function.
So if I roughly go in times, if I repeat in steps in time, then I will get roughly an operator which is a product of in g's.
That's right. So you have this f which depends on this coefficient gamma integrated over all the entire path, and that is supposed to give you an estimation of the cost. Now, you can ask, what is this gamma? I mean, how do I determine this cost functional f? And this functional is not completely arbitrary, and it is constrained. Constrained by these kind of properties. It has to be positive definite. It has to be a smooth function of the gammas, and then.
What does cost mean, please?
Cost mean, you can think of it as how difficult it is to go from here to there.
Difficult meaning how many steps?
How many steps? But here we'll go to the continuum picture, so the length of the.
But it's a discretization of the numbers.
That's right.
It's a continuum version of the
Number of steps. That's right. Number of states with some weight given to each state.
Number of steps. I thought
Oh, steps. Yeah, steps.
Is it just the number of steps? The minimum number of steps?
Number of steps. That's true, but the fact that in this, the qubit information that I'm using very special gates has to be put in some other form. In this continuum picture, that comes to with the metric, that some direction, if it's a 3 qubit direction, I'll call that a hard direction, and I'll increase the cost. And some directions which is 2 qubit, I'll make it the metric small, so that is distance in that direction is small.
I see. How you compute it is one thing, but I'm just trying to understand what it is. It is a way of capturing the number of steps.
Number of states in the
It's
continuum.
Number of steps.
That's true.
Yes.
That's true.
Yes.
A number of 2 qubit operation, or number of, not all kind of steps.
Times you have to act with unitaries to go from one to the other.
That's right.
And there is a likelihood. Gamma of s is like weighting, that this way of going has some larger probability compared to the other.
No, he's saying that it's the number. It's a discrete number, steps.
I thought your
When you go to the continuum, then this notion of weight comes. But in the discrete limit, it is just the number of steps.
So suppose you want to go from one point to the other.
Yeah, you
but
can go
having
in many
this
ways.
probabilities of making
This would be a large number of steps.
right.
But it also happens to have a large length.
Yeah. But why are we introducing probabilities into this at all? I thought complexity was just the minimum number of steps to go from one state to the other.
Yeah, we will minimize this.
That is like very specific.
I thought that was the definition, right, or not?
Yeah, that's the definition. So this cost function is supposed to, when you minimize, that is going to give you the
So
complexity.
you're trying to compute it using some probabilistic ideas?
Yeah.
So the
So
local-
you define a metric on the space of states.
Metric on the space of states, right?
The
And then
minimum
look at
is the
geodesy.
desired answer.
Uh-huh.
Like you do it with this, but then the minimum answer
Is the
will be
complex-
one that you want.
Cost, yeah, the cost of
The
it.
geodesy too, which means metric.
That's right.
How do you put this metric on this set of states?
Yeah, well, I'll come to that in one
Simple
sec.
gates would have a small metric.
Yeah, and you put some penalty factor, this P.
Not allowed ones are these hard directions.
Yeah, this P would be large.
Large distance.
Right, so you can take this functional to be, for example, so there are some,
It's like
Right, but given a path,
Mm.
Likelihood is not an issue.
given a path, it's the number of steps you need to go along that path.
yes.
Steps is a discrete thing, right? If you want to put this in all in the continuous.
in quantum mechanics, you'll have,
Why can't we just say that?
And
it's
then
some-
among
it's
those
some-
parallel
you
paths-
just draw some path and measure this in length with the new metric, and you minimize that length.
so
The
maybe,
minimum length is the complexity
But this is meant to be a continuum version of
of that. Yes.
number of steps.
Number of
That's
steps,
right.
Yes.
that's
This path is in the space of states or these B operators?
no, not anymore in the space of states. We have promoted it into, so any state you can be obtained by acting from the reference state with some operator.
Going from V0
So-
to Vs through this path.
That's right. That's right.
Wait, so just to understand, is there some probability introduced here as a computational device or not? It's just, are you computing number of steps or is there some probability added in the game?
No, I don't know what probability, but there are weights introduced, which has to define which step is more expensive step and which is the.
It's just that to go here, you need more steps than to go that way. Is that right?
Not just that. These steps are made up of gates. If you have only 2 qubit gates, but in general, when you're looking at a trajectory in the space of states, that might be a 3 qubit or 4 qubit process. It might not be an elementary gate. This is what I'm saying. So elementary gates have some cost associated with them, which is less compared to.
Wait, your definition was how many elementary steps you need to make, right?
That's
when
right.
you build a compound thing, I think of that as compounding many elements.
That is fine. When you go to this state picture, you're converting this problem into a geometric problem.
Yeah, I'm just trying to understand. I mean, are you changing the definition, or you're trying to give a way of solving your original definition?
You can say this is specifying a way of the original problem was very ill specified.
I thought the original problem was very well specified.
No, but for continuum systems,
I also like discrete updates because that's something that I understand.
we will see.
What is this S business? How did the continuum?
S is so the gates G1 to Gn. Instead, you can think of this parameter as being promoted to the continuous parameter S, 1 to n, this index.
I don't quite understand how I can. I mean, it's a.
So if you use discrete steps, right? So how long are you going to use?
Yeah, so that is one. This is what I wanted to.
Increase that step smaller and smaller and smaller, and that you
Let's say you have. Let me give you one example. Let's say you have two.
Yeah, that's why it's continuous.
Let's say you have 2 spins or quantum spins, and let's say I'm defining an operation which is e to the minus I x0 p0, something like that. But it also depends on how much you're evolving. So that epsilon, so that gate length of the path is also important. The quanta of the path, the step size.
You have many. I'm really sorry for something else. But
No, let me just finish. So the number of steps is a function of how big the step is. This is all I'm trying to say. Unless you tell me what is the step size, I cannot estimate the number of steps.
That's fine. But first, you had many different possible unitaries you could apply at any time, right?
Right.
Where is that information going into your?
So many different, you mean different paths, many different directions you can start? Is that what you're trying to?
In your discrete problem, you could have, on a 2-qubit system, you could have, let's say you give me a set of unitaries you're allowed to evolve by.
Sure.
One of them could be sigma 1, sigma 1.
Right.
One could be sigma 1, sigma 2, and so on. You specify a set of unitaries.
That's right.
Now, how does that specification go into your Hamiltonian?
So the Hamiltonian, you can think of it as,
Hamiltonian is 1.
no, this is not, this gamma is supposed to give you, some kind of direction in the,
What is that h of s?
H is, you can think of it as the tangent.
Can I say one?
Please.
So see, we want to say that there are all possible unitaries, but I have a bias for my reference set of unitaries. This you can achieve by saying that if you want to use other unitaries, that is a very high cost in your action. This is one way of saying that these are the unitaries that you use to go from here to there. And once you use this set of unitaries, you measure how many unitaries you need and find the minimum length. That will be your complexity. But you need to first specify what is the set of your unitaries.
Yes. So like in the 2-particle Hilbert space, I specify 5 unitaries.
Yes, so that is one specification.
Okay.
Now, if you give me the space of all unitaries,
Yes.
I want to find a way so that I specify that these are allowed unitaries. So I will give you a measure that if you use wrong unitaries, then they are costing me more
Okay.
in the action.
Okay.
So that is like saying that this is my set of unitaries you use.
Okay.
Once you use those unitaries, find all the paths and find the minimum one. And the length of the minimum one with those unitaries will be your answer.
And this cost function is a local cost function. You're saying just in the local Hilbert space, so local times.
Yeah,
how
that's,
many times? Okay, thank
that's
you.
right.
That makes sense.
So there are some, this function f cannot be completely arbitrary. There are some constraints. Triangle inequality has to be homogeneous function of all the gammas, positivity. So these restrict you.
Does that always mean that it has to come from a metric, a linear metric, with these conditions?
No, these are just examples. These are not like, there's a couple of examples I picked up. One is usual familiar, you know.
Basically, you want a functional,
Yeah,
right?
that's
One
right.
tangent space direction, it needs to give you a cost.
That's right. That's basically it.
And that functional, is that a linear functional? Because the linearity is not one of your requirements.
No, there's no linearity. I didn't put in any linear requirement. These are just examples of costs which you can use, and you know, each of them has their own merit and demerit. So complexity will then give you this minimal geodesic. The length of the minimal geodesic is supposed to give you the complexity. Okay. So, but one more thing before we go to quantum field theory, which I will do on the lattice. This is mostly from the paper by Jefferson and Myers, which is why they set this up. So the idea is that, again, you need to give how big a step this is in order to know how far you have reached, how close to this. In some set of states, you have some radius. So it will depend on how close you are, what is your step size, okay? So if you reduce this, you might have to do 2 more steps or something like that. So the accuracy, you have to introduce this parameter epsilon, which is called the tolerance. Without this, you cannot define complexity. And the reference state which we will be taking is that you have n, you can think of field theory as the infinite number of harmonic oscillators localized on lattice. And then you can consider a state in which you have the Gaussian localized at each one of them. So you can take this to be this unentangled state to be a reference state, and then
So the definition of the complexity that you just gave
is
was
high.
about the state going from, was about going from one state to the other state in the Hilbert space,
Right.
not quite about encoding the unitary itself, right? Because that's
That's
different
right.
thing. That probably is a very fine operation,
That's right.
Because this is just an element of the matrix that you want it to be that. Right? But
That's
there
right.
you say u minus g1 g2, so there you are encoding the unitary itself. So what is it? So I should think of the unit complexity.
Yeah, you should think of U to be the thing which I am after now. Yeah, that is my revised goal. You can think of it.
Meaning it doesn't depend on the reference state.
No, it depends on the references because these, you need the reference state to go. U takes you from some reference state to the other.
I see.
Once you have fixed it, then U becomes my.
Oh,
Once you have
I see.
fixed the reference
it's
state.
not going, so it's just from state to state.
Yeah.
Because you could have, another way would have been just to encode the unitary itself, right?
That's true. Arbitrary unitary transformation. No. Yeah, sorry. If I give that impression, then I'm sorry about that. So the kind of complexity for the states these people have worked out, which are easier to do, is this Gaussian
So
state.
in that norm, then is it u minus g1 to jn acting on reference state?
Good question. So this.
How accurate you are measuring the upticks are and all that?
Um,
Acting on the reference.
Yes, I'm not sure right now whether it's the target state or the reference state. Yeah, actually, I'm not sure. Sorry. It could be the target state. Yeah, but since I think I would say what my impression is, it has to be the reference state because the target state, I don't want to. Yeah, I don't want to make it a function of the target state. This has to be with respect to you evaluate this on the reference state. Yeah, then it would be too arbitrary if I change this for every target state. So the kind of target state I'd consider a subset of the most general states, which are like entangled Gaussian. So you see harmonic oscillators in different sites are entangled. So this is the kind of wave function I will take. These people have taken, not me. And then we will use the specific kind of gates, which are.
What is the rationale for this weird looking psi t? I mean, psi r, I guess I can understand maybe.
Because for them, this is then it is.
Like that also.
Yeah, for the arbitrary state, it's a very difficult thing to do. For Gaussian state, it's somewhat manageable. This is the only reason. There is no. If they could do it for an arbitrary state, they would have done it. So for Gaussian, this is the thing.
Also, psi t is more natural if you have a theory. This is more likely the ground state, roughly like ground state, where you have at least entangled between pairs.
But there's some locality or not?
At the saying if you want to think that what
Omega
is,
AB, is it local?
Yeah, so you can.
Capital omega AB.
I imagine
Yeah, it depends on this. Is A and B are the lattice sites.
Next to each other.
You can take next to each other, yeah. Or
So this is not entangled there, but just.
no, no.
maybe
Actually,
it's
I'm
left
sorry.
side.
No, you can take them to be non-local.
then that would be not
And then
So
Q.
some omega.
Yeah. Just think of them as harmonic oscillators, yeah, and there's all n of them are entangled in this, in this wave function. And then the gates which I'm going to use are these kind of gates. Again, this is n by n matrix, which are called scaling and entangling gates, which are the form I wrote down, x0, p0, or if you consider harmonic oscillators, qa pb plus pa qb, something like that. These kind of gates, which you can show will take you from this kind to this kind. If you can check operation of this on this, you will take that you get something Gaussian, but now it gets mixed.
Wait, MAB is something specific.
Yeah, maybe for if you just take two harmonic oscillators, so it will be Q1 P2, P2 Q1, something.
And what was that omega prime please?
Omega prime is if you start from this and you apply this gate, you get to a new omega prime. So the mixing changes because you apply this
So that's the omega prime is the action of Q
on.
site.
That's right. That's right.
And if you can make omega prime diagonal, then you go to the psi reference state.
Yeah, so that's one good way of doing it. You can diagonalize this, and then you directly, you find out what unitary transformation. Yeah, that's one way. This is done in the paper for 2 by 2. So if you choose some convenient parameterization, so these give you some kind of GLNR action on the space of states. Omegas, this give you a GLNR transformation, and their idea was to take this GLNR transformations in the space of GLNR transformation. You're supposed to give out a trajectory, and they have some particular parameterization in GLNR, and then they compute this geodesic, extremize it, and you get this kind of an answer.
What is the metric? Is the standard Cartan metric or something like that?
No, not standard Cartan metric. We have to use penalties and costs.
So what is some choice?
Some choice of metric, yeah. So what is unpleasant about this is, so you never know whether the answer you obtained is a function of the parameterization. The way I would like to set up what Balasubramaniam and others have done is to not use the geodesic equation in some parameterization, but this thing called the Euler-Arnold equation, which is a general geodesic equation for Lie groups in which just the structure constants appear. So that is a more parameterization independent way of defining geodesics and trajectories. But I'm not sure for GLNR.
Sorry, but once you've specified your QAD, then the answer of how many steps you need to go from one state to the other is in principle well posed. And now the rest is your mathematical abilities.
That's right, basically.
And can you explain even roughly how you convert this into some metric problem? You've given us this MAB.
Right, so MAB, this you have, but MAB now you will need, let's say, n number of MABs you need to get to your, so those, for those MAB I need to define an MABS, this kind of number, the step, and then some kind of cost which depends on the F, the metric, and then I integrate.
How do you compute this cost?
That has to be, that you do only if I specify an F. So they have considered some.
But once you've given this epsilon QA, PA minus plus PA QB, the answer is now determined, right? There's no freedom.
So I think what's going on is that first 4 points carve out a finite dimensional subspace out of this infinite dimensional input space, and on that finite dimensional subspace, the unitary is now this GLNR, not unitary, but there should be U, I guess. But and there you are solving.
No. It's not unitary anymore. Now we're focused on not the Q but the M. M is not unitary matrix.
Yes.
M is not a unitary matrix anymore. So the M is that's why it's an invertible matrix, but it's not a.
But is it not true that now this problem is being solved in a finite dimensional input space?
Yeah, it's an n by n matrix.
Yeah. And then you still have to specify on that Hilbert space what is the cost.
Cost function, yeah.
In a tangent space direction.
Right.
In the tangent finite dimensional tangent space.
That cost
And for some cost, that is the answer.
No, but I don't understand why you have to specify anything. Because if these are your only operations allowed.
No. So those operations will definitely take you to that.
No, there are many
He has,
ways.
First of all, restricted himself to some very special type of target spaces, and then he's saying that there are this QAB, right? And QAB does this kind of thing on transformation on omega. So now the problem now is to go from one omega to the other omega using Qs.
Yes.
But now what Qs do you use? Qs still will come with the ATCs AB.
Yes.
So now you.
And there are many. It's not a unique.
Direction, more preference, 3-4 direction, less preference.
And it's not unique. So this.
But why preference? I thought you just counting the number of Qs, the times you have to act with Q to get from one state to the other.
No, but you can do that in many ways. See Q1 to the 3 times,
Find the Qs that takes
Q2, 3, 4 times.
Many omegas are different. So you have to act with many different Qs. These are just two particle Qs, right? Let's say that we've got.
Yeah, they involve like 2 oscillators at a time.
But all omega AB are general non-zero.
Yes.
So you can't do it with one set.
But you can still do it in different ways. Q1 to the 8 and then Q1 to 2, 3 to the 2. There are non-unique ways of writing this.
I'm trying to understand, is your definition the number of times you have to act with this Q operator to get from one state to the other, or your reference state to your whatever state, or is it?
It would have been if there was a single Q. There are many Qs, 1, 2, 2, 3, 3, 4.
Exactly. So I thought.
And then it's non-unique.
It's not unique, but
Number of
I'm looking for
steps.
the minimum number of steps needed to get from one step to the other.
That's right.
That's what you're looking for.
That minimum number, instead I'm going to compute by some trajectory.
This is fine. But once you specify your Qs, now the minimum number is a well-defined mathematical question.
That's true.
There should be no ambiguity about there should be no ambiguity in specifying your cost function, right? You should
That's
be able to
true.
compute it. So I can't understand when you keep saying you choose one cost function and you choose another.
Yeah. I think it's probably the
I see what you're saying. That maybe yeah. So I see what you're trying to say. If I had included,
same as 3-4 direction. That we still have to take it, right?
Yeah, I'm saying that all operations are equal,
Right?
right?
Yeah.
Yeah.
So that's like the Cartan method.
Yeah.
I don't know whether that is the answer.
right. So 1, 2, maybe 1, 2 is special. Although it's a subset of 2 qubit gates which you are making special. Only then can you apply this cost function. Yeah. Once if you just restrict yourself to these gates and they're all equal, then then there is no ambiguity.
And
Is that the answer?
Yeah. This is the answer. For example.
once you choose this minimum number of gates, all gates are
Yeah.
democratic, then you can calculate and you find the
Yeah, and you can see there are no cost numbers appearing here. These are all, A is like the lattice spacing, N is the number of degrees of freedom, D is the regulator. So not lattice spacing, but lattice label. And this is the difference between the two lattice sites. M is the mass. So this answer is independent of the.
Information about omega also, right?
Yeah, the omega is M. I have taken omega to be the M.
No, but the capital omega AP, it should have some information about the target state.
Right. So it was like omega squared. So this was this plus something else. So I have taken some kind of expansion of those. Yeah, I should. So the final answer is something like this, but I've written in omega tilde square by omega square 1 plus log of this, something like that. But this omega tilde I've written in terms of omega. That's why it has gone away. So this I've only copied the final expression from their paper, not the intermediate where you have this omega tilde, which is the time.
You wrote omega tilde in terms of omega.
So omega tilde is,
There is a specification.
no, they took nearby states, so omega plus something.
So this little a is the site label and delta is the
Lattice spacing. That's right.
Where have you specified your final state? In the answer, this is I'm just repeating Abhijit's question.
Yeah. So
Where is the specific, what parameter that labels your final state?
that final state was some special final state. It's not a generic
Some particular.
final state. Yeah. Some particular.
namely that capital omega AB is what for this result? What was capital omega?
Capital omega, I don't remember the exact expression. I can look it up. But this was some special case. Why I chose this particular expression to display is I wanted to show that it depends on the regulator. So So the answer does indeed depend on omega prime. This is some special case which I put this one because I wanted to display the dependence on the regulator. This is not not something in quantum field theory which you would consider usually, because it's a regulator dependent quantity. So this is what I wanted to. This is the thing highlight which I wanted to show. Of course, it depends on the final.
Yeah, I'm not surprised by that, because the number of steps that you have to take in order to go from your initial state to the final
That is
state
different.
clearly be more and more depending
Refined,
on
but that is in the space of states. This is in the space of in physical. This is a regulator in the physical space-time.
You mean the lattice spacing? Is that what you mean?
Yeah, yeah. This is not the tolerance which I.
So where is the tolerance in this?
Tolerance is not displayed here because I've chosen it here, so it doesn't.
Because if I take the tolerance to 0, I'll expect the complexity to go to infinity.
Complexity to become infinite or something.
Yeah, but I mean, if I want to see from this expression, what should I do?
Here you don't have the tolerance appearing, so we've got rid of it. So once you fix the tolerance, the answer is fixed.
But in this whole problem, never did lattice spacing appear.
No, so Q1 minus Q2, the difference, you can think of it as that Q1 minus Q2. You can define this to be those parameters will appear in the omega.
Okay. So in the nearby state, that's what you mean.
Yeah, yeah,
That the next nearest or something like that.
something like that. Oh.
Oh, I see.
Okay, so somewhat of an extended, but let me come to our story, which is less. So, generally, the message is that it is very hard to define complexity in the continuum limit. People have tried, but there's no unanimous way of doing this. So, however, unrelated to this problem, which is to define complexity in the continuum limit, what in holography, what Susskind had proposed is that the complexity, however you define, is giving you the maximal volume slice, some maximal volume slice in the bulk, divided by these constants, which are for dimensional reasons. G Newton is the Planck's constant, of course, and RC is some characteristic length scale. It is not specified even in this definition. So, if I can go back briefly to the Einstein-Rosen bridge picture. Let me just, sorry. Yeah, so if I may go back, so this is the maximum surface, and since the volume crunches near the singularity, you would expect this maximal surface to crunch as far as to be repelled by the singularity. And the more closer to the singularity you go in time, the ERB will get repelled more and more by the singularity in order to maximize the volume. So you might think that this project is not very well defined because complexity should not know if it's the maximal volume. It should never know regions of crunches, because it stays away from the singularity. So now perhaps you might think that there's no obvious association of black hole singularities and complexity.
What is RCA?
RC is some characteristic length scale. For ADS Schwarzschild, it is the ADS radius. For normal Schwarzschild black hole flat, this is the Schwarzschild radius. This is an arbitrary, it's an unpleasant feature, but it is there for dimensional reasons. And the way you determine what this is, if you take dc dt, if it only gives you Ts, which is m, if you put the correct length scale, only then it will give you m. If you take something else other than that, then it will not give you m. So this is how you fix this. So, however, there is this.
So let me go back to the question that I asked some time ago. So in order to define, the proposals about complexity being the volume of this Einstein-Rosen bridge,
Right.
Depended on the direct product structure of the Hilbert space and having to do with the entanglement between this.
That's right.
But so far, the definition of the complexity that you just talked about
In quantum field theory.
That structure in quantum field theory.
No.
So you want to specify something more. When you say complexity here on this slide,
Yeah.
you don't mean the one that you talked about just now. You mean
This is what I said. This is maybe what we have defined doesn't capture, because if you compute, they don't scale with volume, which this part will scale.
No, I
So.
mean, what is the entanglement business? How is the entanglement business coming into this complexity?
So
Between two things.
So let me just say why I feel this is the case.
So this sigma max is presumably some surface from one side to the other, right? Or something like that.
That's right.
Maybe the reference state is unentangled between the two sides. And the The unitary operations allow entanglement.
It goes in through the definition of what are allowed operators.
Allowed operators, and what was the reference state? The reference state was completely unentangled between left and right. And the allowed operators allow some unitary that mixes the two. Then you can generate entanglement.
Okay, so you might assume that there is no association between singularities and complexity because it stays the maximal surfaces stay away from the singularities. However, if you remember the firewall story, what happened was that the late Hawking radiation inside and outside entanglement, infalling and outfalling, the entanglement breaks because you want unitarity to be preserved. So you want it to be entangled instead with the early Hawking radiation. And this lack of entanglement rate led to the appearance of firewalls, which is a kind of naked singularity. So in fact, indeed, lack of entanglement, indeed, there is an intuition which led us to believe that can lead to singular spacetimes. So for example, in firewall. So so this is the intuition why we feel, despite the fact that it stays away from singularity, there is some association. And then another related development, Susskind also proposed that okay, this definition is somewhat, it's not. There is an alternative definition of complexity, which is in terms of the action evaluated on the so-called Wheeler-DeWitt patch. And here you have some universal constants appearing. There is no characteristic length scale. So it's a much more universal-looking formula from the bulk perspective. There is no characteristic length scale. It's just action divided by pi of h bar.
What is the Wheeler-DeWitt patch?
So the Wheeler-DeWitt patch, I will draw this in later Penrose diagram, but let me just, if you have, this is your boundary and this is some time, then the Wheeler-DeWitt patch is you draw light rays on all directions, and Wheeler-DeWitt patch is this region inside the light cone.
And if you have 2 points, they set up the inside.
Yeah, 2 points. The idea is it's the union of all space-like curves joining T1 and T2. So these 2 points, you draw all possible space-like curves joining them. The union of all this is the Wheeler-DeWitt patch. So this is a much more nicer looking formula, more universal looking. However, there are some complications. When we give an action, we all know that, especially actions evaluated on things which have boundary, is complicated. In order to make them all kind of diffeomorphism invariant and all kind of invariant, you have to add, every time you have such corners or edges, you have to add counter terms in order to regulate, because otherwise the action is not well defined. So although it looks from universal, there are also issues with this.
And the Wheeler-DeWitt patch can sometimes hit the singularity?
The Wheeler-DeWitt patch will hit the singularity. Yeah, so the singularity, so it will get a finite contribution from the singularity, this boundary term. So it is bounded by the null cone, light cones, and then on one side it is bounded by the singularities. So indeed, it does get a contribution. So this is what I have in the slide as a finite contribution from the singularity. Despite that, the CV answer will match the CA answer, which stays far away from the singularity, and the CA answer, which is the action evaluated inside this with the boundary terms. Despite appearances, they will match. At least in the black holes, all the kinds of black holes they've considered, Reisner, Nordstrom, Schwarzschild. You can also consider the Y-diametric and the collapsed black hole.
You just mean V matches A.
Precisely, not just V. You have this V divided by this. So that thing matches A.
The C equals any of this is still yes proposal.
Yeah.
So the contribution of the singularity to the action is finite?
Is finite.
Finite or zero?
No, not zero. The measure is zero at the area measure is zero, but then
The boundary terms of singularity will give you a finite contribution?
finite contribution.
But you trust it anyway.
Huh?
But you trust it anyway. It's
Yeah.
finite number, but you trust it coming from. Okay.
Yeah. So they match perfectly. So C, V, and C. This is what gives you can think what gives them confidence to say that they are it's not something nonsensical. So now this was all black holes. As Gautam said, this is a very specific example. Should not draw general lessons from this. So for this reason, people wanted to look at other kinds of cosmological singularities. And the specific kind what I'm going to talk about are these singularities which arise in the bulk, because you have a specific kind of CFT deformation. So what you do is you take time-dependent deformations of CFTs. If Sandeep was here, he would probably know. He had written some papers on this, in which, let's say, you take n equal to super Young-Mills and you make the coupling constant time-dependent. Not only that, they will blow up at some finite time. So this, you do something wrong to the CFT, which is why the singularities arise in the bulk. To preserve UE completeness, we only allow for such couplings which we are going to make time-dependent. We only allow marginal and relevant deformations, right? So we don't want to destroy UV completeness. So marginal couplings would be marginal such kind of deformations would be examples in which you make the CFT couplings time dependent, or you put the CFT on some boundary metric which has time dependent. For example, you could put the boundary metric on Käsner, and then the ADS Käsner would be the dual geometry, which has a singularity, of course. Another kind in which you put the CFT on some R1 comma D times another circle, and then the circle pinches off at particular points. The radius of the circle it depends on this location. At some point becomes 0. So you get singular points, and this will also lead to singularity in the bulk. So this will lead to some kind of I don't have the Penrose diagrams here, but this is the metric. This is basically the idea of the metric, bulk metric. So you have these are the holographic direction, and this is the boundary direction. Spatial directions have time dependence in them. For example, for the Käsner case, you can see for some values of some non-zero zero values of t, this becomes singular. The metric becomes singular. For the topological crunch, this is what I was talking about. The circle radius is a function of t, and at t equal to 0 or pi by 2, you have t equal to pi by 2, it becomes singular. It becomes 0. For the relevant, you can also do relevant deformations. This would mean that you introduce time-dependent mass scales in the CFT. So, for example, something like this. So you have a mass term, which again it becomes 0. It becomes right. Maybe it should be yeah. Sec becomes infinite. Yeah. So it blows up at some finite value of time, and this leads to in the bulk, it leads to kind of this. Let me just draw this. So the boundary interpretation of this, bulk interpretation of this relevant deformation is a bit weird. What you have is a domain wall in the bulk separating two ADS regions. And this domain wall, when it reaches the boundary, you have a singularity starting from there.
Sorry. Question about the previous thing. If you used either of your definitions in a black hole diagram and you computed the entropy as a function of time, it just keeps increasing with time. The complexity keeps increasing with time.
That's right.
Without bound, just keeps going.
Yeah, I mean you're computing the late time complexity. Of course,
yes.
it captures the geometry, so it will keep on increasing. It doesn't see the plateau region. You don't see the plateau region.
You don't see the plateau region because that we expect to happen at some time of order n square or something.
Right. So you don't see that. So this is the metric in the bulk which corresponds to this introducing a time-dependent mass scale in the CFT if you introduce that. So this is the point in the boundary where this domain wall reaches the boundary. You'll have a singularity starting from there. So you have two ADS region and then the space-like singularity. This is the kind of again this is not a horizon, so it's a naked singularity. So these kind of naked singularities were what we considered. And we estimated the complexity. You can compute the extremal volumes in this case, given a time, what is the extremal volumes. And for the ADS Käsner, you have this kind of an expression. What you can see, this is the this is the IR regulator in the bulk, lambda, some large radius. And of course, it gives you the right, it's extensive. And then this is what Shiraz was asking, it grows linearly with time. So you see the linear growth. All of them will have this, some increase in time. So this one actually is diminishing. Again, you don't have a time-dependent expression in this case. Again, so all three, what it tells you is that complexity actually t equal to 0, near t equal to 0. Let me draw the Käsner case. As you approach the singularity, so let me just maybe I have every case. Complexity decreases as we approach the singularity. So for example, in the Kasner case, it's true it's increasing with t, but at t equal to 0 is the singularity. So if you go away, it increases. That means that when you come closer, it actually decreases. So all these singularities, you have this common feature that that complexity actually, this is again a decreasing function as you come closer to the singularity. This is also a decreasing function of t, and t equal to 0 is the singularity. So the unifying theme of all this is the complexity indeed does decrease as we approach the singularity.
This is a singularity in the field.
Yes, but also in the bulk as well.
But your problem is about computing in the field.
That's right. But here we are computing just using the CV formula. So there is no bulk boundary calculation of this. So CA you can also ask. So again, you only develop partial confidence if it's just CV. So you also need to compute CA to see if this is really the case. Again, CA gives us the same kind of an estimate. You can compare next to each other. I've written down. The only difference is this coefficients, actually, that's why I've written the similarity sign and not equality, is that there are numerical coefficients which differ. Although the qualitative structure remains the same, but the numerical coefficients, 2 by 3 or 4 by 5, d-dependent constants, they appear, which I didn't bother. Yeah.
Don't get the logic. So you said in order to get confidence.
Yeah, I mean, it could have been. So that CV is equal to CA only in the black hole case.
Okay.
How do you know for these?
Confidence for what statement?
That there is some, CV and CA are giving you some universal notion of complexity. Like they're not completely different things. Complexity is a state-dependent thing. There are many ambiguities in complexity. Maybe CV and CA. So this is what first thing we want to make sure is, they are the same thing. For the de Sitter crunch, we computed dCdt, and this remains the same. However, the expression looks slightly different. They're big. That's why I didn't write them on the slide. So ds crunch, what we see is that the leading terms are different, and the subleading terms are also different. So in this case, the situation is a bit anomalous, because for this case, let me just go back. You have the situation, but in the CA, the calculation, this looks a bit different. So, but it looks different, but the qualitative feature that it decreases as we improve the singularity, that remains the same, although the expression is a bit different. Not only that, for the subleading terms will also give you, they are also a bit different. So subleading terms are different is a generic feature. If you look at all this case, you have this function. However, if you compute CA for the topological crunch, the leading are same, but the subleading terms, they look slightly different. Okay. Then this is true for ds crunch from the very first order itself. Leading order itself. Subleading terms are not different, but the leading terms are also different. So the lesson which we draw from this is that what are the universal features of this? Complexity monotonically decreases, and this is because we understand why. Because the CFT volume, we did something to it. The volume itself, CFT volume crunches. That means there's no degree of freedom left.
Sorry, I didn't quite understand this. Why does it happen?
Think about it. Think about the CFT as some discrete number of degrees of freedom put on lattice sites. And then when, for example, you put the CFT on Kasner, the volume crunches. So you're entering some kind of area which is in between lattice sites. There's no more degrees of freedom there.
What if I just put the CFT on standard is 3 times hard?
Then also because the volume crunches. No, I'm not putting the CFT on standard volume. So let me just go back. Maybe I was not clear here. So you put the boundary metric. This is the boundary metric, and this Hij, this becomes 0.
But when the size of this volume or the CFT leaf is smaller than the lattice size, you don't trust your theory.
Yeah.
That means that the degree of freedom goes to 0.
You don't have any degrees of freedom in your theory anymore. This is the interpretation. So the time rate complexity contains the UV divergent piece for this dependent piece for CFT, metric being time independent. So these cases, the UV divergent, there's a, the rate of change is UV divergent, In this case, the rate of change is not UV divergent. Let me just. And the coefficient of the rate of change is actually determined by the sublating term. This is another universal feature. That's why this is true for all three cases we considered. The rate of change is determined by the subleading term. This is reminding us of the CA case, in which the subleading piece was from the singularity, from the surface, that it was determining the rate of change.
So in this part of the talk, do you also have two boundaries?
No, just one boundary.
So this is complexity
Of the boundary state,
of the boundary state.
with respect to some reference state, reference boundary state.
Okay, but now it's going to be a very different reference boundary state, because I had thought roughly that the reference boundary state was something that is decoupled between the two sides.
Right. No.
Now there
Now
is
we
a
don't have two
second
sides. Yeah.
Yeah.
So what are the lessons of the story? Perhaps these two bulk geometry constructs, the Wheeler-DeWitt patch and the maximal volume, they're two different CFT complexities as well, because they don't exactly agree. And the universal feature of decrease of complexity actually contrasts our experience with the usual way of probing singularities, which is through local probes, like point probes, like strings. These experience extreme blue shifting when you, there's back reaction when you put them close to the singularity, and as a result, things go out of control. However, these, the way complexity sees the singularity is very tame. It goes to zero, it diminishes to zero. So the way, the way we see singularities with complexity is completely antithetical to the way our experience with local probes. And because there are some universal features, perhaps one can attempt a parallel with the classic BKL work regarding the universality when you approach a singularity. So, okay, this is an open question. This is not BKL is this Landau, Kalatnikov, and I forgot who this B was. That if you approach the singularity, if you do GR, like you're not doing perturbations near the singularity, then there are some universal features the way you approach to the singularity.
Spatial kinetic terms go to zero. Take a minimally coupled scalar equation, you go near the singularity, and the spatial kinetic terms go to zero. So it looks like each point is decoupled from the other.
Yeah, something like ultra local, yeah. So maybe one can do a much more bigger investigation in which we try to reproduce some of their. Anyway, so moving on, this is the real thing, these are all older topic. What I wanted to talk about today is a recent work, which is regarding time-like singularities. So if the reason we looked at this is because our collaborator works a lot on these holographic theories of condensed matter systems, holographic descriptions. Solutions to such effective holographic theories at zero temperatures typically have naked time-like singularities. You can see this in many ADS-CMT systems. And such singularities are that the folklore is that such singularities are generically resolved by lifting them to higher dimensions. So not effective, but if you in full string theory, they are not singular, or by eventual inclusion of stringy states or branes.
So good, just backtracking. If you look at your I just want to understand what lesson you might want to draw from this claim that when your space-time volume goes to zero, your complexity goes to zero. So now, everything you're doing is some unitary transformation. Let's say you start with the.
Oh yeah.
You start with the space-time being nice and big, and time dependence is some unitary transformation on it. Unitary transformations preserve the dimensionality in the Hilbert space. Right? So, if you've got many different states, you also go to many different states. So it's not like your Hilbert space is crunching to zero, but it must be somehow that you're evolving into some states that are very near to the reference states.
I see. I see.
Very simple states somehow. And
this is why complexity becomes
must
zero.
be, right? It must be something like that. So I was just trying to understand, do you have any rough idea what your reference state is?
Yeah, it has to be some, the way you set up the question tells me the answer, that is that the reference state must be something which is unentangled, because
each point is unentangled.
Unentangled, yeah.
But it could also be that the unitary operator is small. It's just nearby unitary operator. It's an operator, not necessarily an element.
I didn't understand.
I mean, just that whatever one way to interpret this could also be
Wait, sorry, I didn't understand. How is that connected with the statement that when the volume scrunches, you're going to zero?
Yeah, because no matter what reference state you choose, you end up nearby because the operator is close to it.
No, but the state.
I'm just trying to see it could be a reference state independent statement also.
No, I mean, we got
I
a
don't
big
think
Hilbert space initially,
Yeah.
when the volume was big. Each of those states is evolved to some state.
Yes.
And presumably the claim is that all of them are independent of the details of the initial state, or just the vacuum, or the vacuum. What is the claim? The complexity of which state is going to zero?
Complexity of the CFT state, which is dual to this geometry. So this is
which was some simple state originally, like the vacuum.
could be, yeah, could be. I mean, I'm not so sure whether it's a vacuum.
Or you could figure it out, right? Just look at the geometry at very early times.
And yeah, if you look at the geometry of very early times, and if you compute the complexity and it turns out to be zero, then I would say, okay, because the complexity is zero, this might be the reference state.
Yeah. Okay, so sure.
So there is
the vacuum. You're driving the vacuum to something near to your reference. At least originally, the vacuum required many steps to go from your reference state to your vacuum, because the complexity of the original state was not small. But now you're going to a state where you require few steps to go from reference state to vacuum.
yeah. So that I would agree more. So at t equal to 0, if it's a complexity is a large number, it's non-zero, then your reference state is certainly not the initial state, even though if you take it to be vacuum, because the complexity is large. For pure radius, for example, complexity is non-zero. If you evaluate pure radius,
Exactly.
so that means that your CFT vacuum is not the reference state.
Yeah. So as you said, if you sort of try to unentangle things locally, that would be very far from the original vacuum.
Yeah, which is completely entangled.
Yeah. Of course, if you can make that somehow precise. Okay. Thanks. Sorry.
You know, for a free scalar field, starting from a very highly excited state of very high energy,
Right.
you know, you evolve it, and it would go towards some high temperature, you know, kind of state. What I mean to say is that it would be like some gxy, phi x, phi y, exponential of that, and the gxy will be cut off by the thermal wavelength, which will be very small. So if you start from a generically very highly excited state,
Right.
you would imagine that at large times
There is
it
some
will go towards a
very simple
sort
state.
of, decoupled.
Right.
state.
Oh, yeah. I was not aware of
But
this.
This is an example only from
Just
free
not even a
scalar-
CFT.
free
Yeah,
scalar
yeah,
field.
free scalar.
Yeah.
I
And
see.
you'd have the hard time making this precise in the continuum field theory language. Okay? Because one of the lessons that the information theory people keep drumming into our heads is that there's no state in the Hilbert space where local degrees of freedom are unentangled.
Oh, yeah, that's true.
Okay.
So what you would say is that the dual of all those would be like these kind of naked singularities, all those states, all those high
I was
energy.
just making a field theory statement,
I
try
see.
to see how the complexity can.
In what circumstances can this
progressively decrease
Right.
in time, starting from something
some
which
generic?
I can recognize. So,
But
Right.
where was the temperature in his you have temperature also?
Like final size of the mass.
yeah, this omega AB thing that he has, you know, that would be like a very short range stuff. even
Right,
if you
right.
do those
Yeah.
modes.
No, but in this computation, in the bulk,
In the bulk computation, there is no temperature.
There is no temperature, but you're doing something very drastic to your
background geometry.
to your
Yeah,
background
right.
geometry. That will pump a lot of energy. So maybe that's proxy for it.
Right.
Hmm.
Okay. Just focusing attention to time-like, which are a different class of singularities. They are not considered that problematic in string theory. We have successfully resolved many such time-like singularities. However, we still wanted to look at this complexity characteristic for time-like singularities and see whether we can learn anything. Because, as I said, if you look at string probes and what complexity is telling you, they're completely different. So maybe it's worthwhile studying time-like singularities as well. So.
Why should we say that? How long do we need?
10 minutes. It's almost on the final lap. So for these kind of singularities which you encounter in ADS-CMT systems, there is a criteria which says which singularities are kosher and which are not allowed, or they're really pathological. They cannot be admitted in string theory or the full string theory. So these are given by this criteria by Gupser, who says that naked singularities allowed in geometries. These are those which can be obtained as deformation, the limits of regular black hole. So you regular black hole and take some kind of extremal limit. The kind of naked singularities which emerge as a result, they are allowed. They are fine. You can resolve them in the full string theory. If it's not, then those singularities are really pathological and they cannot be there in string theory. So this connects, you can say, effective field theory and string theory, full string theory. So this criteria, of course, this has evolved. Kuretzis gives some new conditions. So this is not I don't think this is just a theme, but you have to specify it, make it more precise. And the Kuretzis has many more, 4 or 5 criteria, which he has in his paper, 2010 paper, if you look. So just as a test example, we wanted to look at the first thing you encounter about time-like singularity, the most vanilla example is the negative mass black hole, right? We know that is not a good system to look at because it has no ground state. So we know that, but still you want to test what complexity, whether the answer which gives you matches with this intuition or not. So we looked at this negative mass Schwarzschild area just as a warm-up example. So you have this is the Penrose diagram, and then this is the Wheeler-DeWitt patch. So action complexity we evaluated. This has UV divergent pieces, which is the Einstein-Hilbert piece, and then the null boundary, you have some pieces, and as well as from the singularity. There are edge contributions as well, which are vanishing. So this is one. So what turns out is that each of individual piece, although they are divergent, they're all negative. So indeed, they're unphysical. So if you compute the complexity for this kind of a region, all the contributions turn out to be negative. Okay. So negative mass Schwarzschild, indeed, it is unphysical, and also in the complexity, we have reason to believe that complexity is supposed to give you the number of states. If it's a negative number, then it's something really unphysical about the system. So it's fine. So then we looked at a more realistic example, which was found by our collaborator G in this paper. This is like a time-like version of the Kasner radius. Again, you can find these solutions to an exact solution to ADS-Sugra equation. So this is how the metric looks like. So you can see this is this Fz. This is a singularity when z equal to z naught. You have a singularity which looks something like this. So this is the time-like version of the Kasner because, again, as it is anisotropic, the characteristic feature of Kasner is that anisotropic. So you can see this alpha, beta, gamma, these Kasner coefficients. So the spatial regions alternatively, sorry. One of them is time. Instead of space, in Kasner you had all three to be space. Here one of them is the time-like direction. Okay. So the action complexity again it has UV divergent pieces, and this is the same thing as negative mass Schwarzschild. However, even for this physical singularity, which is allowed because it can be realized as some kind of a limit of an extremal black hole, we find the action complexity is still negative. So this is not in sync with Gupser criteria. Okay. So this is the first thing we notice is that complexity is giving you some answer which is contrary to Gupser intuition. So this is not a good sign, and which we will confirm in the next system which we looked at. Now there's some recent geometry which was obtained by G. This is an Einstein scalar system, and the Einstein scalar system has solutions which contain time-like singularities. In particular, the singularity changes, the nature of the singularity changes if you tune this parameter alpha. For alpha less than 1 over square root of 3, Gupser criteria is violated. That is, you cannot find any black hole, finite temperature black hole, whose extremal limit is this geometry. You cannot. So those things are ruled out. So it is not a finite extremal limit of a finite temperature geometry for this kind of a range of parameters. So you would think that complexity should give me something nonsensical, but the complexity for this kind of a pathological range, it turns out to be positive and finite. So overall complexity is positive, but it is not an allowed singularity in the theory according to Gupser criteria. One more thing which we notice is that the complexity has a drastic kind of a phase transition if you cross the Gupser bound. If you go from, let's say, plus more than 1 over square over root 3 to in this side, you obtain a huge change in the complexity. So there is some kind of a phase transition going on which complexity notes records. However, Gupser criteria is violated, but complexity doesn't show any suspicious figure, It doesn't say whether this is an allowed singularity or not an allowed singularity. It doesn't answer that question. So maybe let me just draw an outlook. For time-like singularities, association of complexity with time-like singularities is not so clear from our investigation, what we feel. For space-like singularities, it does have some intuition. For time-like singularities, we do not see that. There's no, complexity doesn't reduce as you approach the singularity or anything. So it is not clear. So this is the, I would say, the principal takeout from this. It is not incompatible with Gupta criteria for the sub-cases we looked at. So another feature I would say, for the space-like cases, we never had negative complexities. For time-like singularities, for example, the time-like Kasner, you get negative answers. So again, perhaps telling you that for time-like singularities, geometry which has time-like singularities, complexity is not a good, as CA or CV, these are not good probes. Maybe something really, you know, so this is our takeaway from this. Okay, so.
IIT Bombay questions?
No, we don't have anything. Looks very different. Complexity.
Oh.
Sorry, I have a question.
Okay.
Yeah.
Sorry.
So you just said that singularity and complexity are like inversely proportional to each other. Can you hear me?
Yeah, I can hear you. I just don't know what you mean by inversely proportional.
If you
No,
go
I
near
mean,
the singularity, complexity decreases.
Yeah. Yeah, if you go to the singularity, the complexity decreases. So can you elaborate on this point regarding the phase transition? I mean,
No, the phase transition has nothing to do with the singularity. Singularity is there for all values of alpha. All values of alpha, you have a singularity. So the idea is that which are, Gupta criteria tells you which singularities are allowed, are admissible, which singularities are arising in effective holographic theories, which of them are allowed in full string theory, full solution of string theory, and which ones are not. So it's the nature of the singularity. It's still a time-like singularity. It has nothing to do with whether the singularity goes away. You don't see a phase transition when the singularity goes away or comes back, and nothing like that. It's in the nature of the singularity whether it can be admitted in string theory or not.
and
Questions here?
So it's somewhat related to what Sridhar was asking. So when you were to say one Planck length goes to the singularity, why do you still trust your calculation?
You don't. We don't. I mean, it is not supposed. We only trust this part of the. This part. You only trust this part. You don't.
If you don't have any questions, could you mute the microphone? Thank you.
Because when you are computing the volume or the action in the Wheeler-David patch,
Right.
you are going till it hits
There you go. But you say that there are other terms which are more dominant pieces.
Okay, so the contributions from the singularity or region very close to the singularity are subleading compared to the first term?
Yeah. So if you have a Planck scale correction, that would be larger. That would be like adding a string to that, or adding a something. Near the singularity, you have very high geometry, so you consider not just the empty geometry, but let's say another string. Then the back reaction will be infinite, and the geometry will drastically change. So then, if you compute CV, that will be.
If I compute a conjecture for Gauss-Bonnet gravity, for example,
Yeah, you
what
can.
do you expect?
What happens is that they are supposed to give you stringy corrections, right? So stringy corrections, then you see this curve actually decreasing. So the Gauss-Bonnet parameter, it's like it decreases the complexity. So this, I think I referred to you a long time back. There was this work by some people from Iran, Ali Shahiya or someone others.